Hello everyone, this is my final research presentation for cse545. My name is Dan Witten and I've been a student in this class for the last semester, and so for my final project I've chosen to explore a hybrid genetic algorithm with the wisdom of crowds enhancement in order to solve the minimum vertex cover problem. I'll be comparing this hybrid algorithm to a standard unenhanced genetic algorithm to see which one performs better in the end. So for our background, we have the competing methodologies, the genetic algorithm versus the wisdom of crowds. So genetic algorithm, what is it? So this is a search method inspired by natural selection. It works by evolving a population of random solutions over many generations using processes like selection, crossover, and mutation. The key element here is that it's random. The genetic algorithm has a strategy of exploration. It's designed to randomly explore an entire vast solution space, hoping to discover a great solution. Otherwise, it is dependent on how lucky it gets. On the other hand, we have the wisdom of crowds hybrid. So this is a strategy of exploitation. It's a completely different approach. This technique leverages the collective intelligence of the best solutions found by the GA, or otherwise called the experts. It finds what these experts agree on and forces the rest of the population to adopt these traits or wisdom. It's not about random discovery, it's about refining and finding the best solutions and using the best solutions that we already know are good. My project is essentially a head-to-head competition between exploration and exploitation. So what is the problem we're applying these two strategies to? I chose the minimum vertex cover problem. As you can see in this diagram, the goal is simple: to find the smallest set of vertices or nodes, which is shown in red, so that every single edge in the graph, or the lines here, is touched by at least one of these red nodes. So you can see with the three red nodes, all the edges are connected to it somehow, and so that is basically what the minimum vertex cover problem is. So we're just trying to find the least amount of nodes that will touch every single edge in the graph. Like the traveling salesman's problem, this is a NP complete problem, which means that there are no efficient algorithms in order to find a perfect solutions for this graph. So because there's no perfect answer to check against, our experiment could have gone any way. The smarter algorithm isn't guaranteed to win, and that's what makes this a very fascinating experiment. So into the experiment itself, the question is, will a hybrid genetic algorithm enhanced with the wisdom of crowds method find a better and smaller vertex cover than the standard GA? So we will generate 5 different test data, graph 20 sparse, graph 30 medium, etc., and these 5 new generated custom connected graphs, as you can see, they increase in size and complexity, starting at 20 vertices, and then it works its way up to 60. These were saved into files, so I could run both algorithms for the exact same data for a fair head-to-head comparison. So let's do a deep dive into our first algorithm, the standard genetic algorithm. This is our baseline, basically our explorer, and it's important to understand how each of these components works for this specific problem. First, we create a population of 100 random solutions. It's important to note that for the vertex cover, a solution is just a list of vertices like node 1, node 5, or node 8. This is very different from the TSP, where a solution was a permutation of all the cities. Next, we use tournament selection. This is our survival of the fittest, basically derived from Charles Darwin. The algorithm picks 5 random solutions from the population, and the best one with the best fitness, the smallest, most valid vertex cover, gets to be the parent. Once we have 2 parents, we use uniform crossover to create a child. We go through every vertex in the graph. If a vertex is in both parents, the child inherits it. If it's in neither, the child doesn't. If it's only in one parent, there's a 50-50 chance. But this crossover creates a massive problem, which is the biggest single challenge for this project. A new child solution is always going to be invalid. It's just a mix of random vertices, so it fails to cover all the edges. That's where the greedy repair function comes in. This is the most critical function in our baseline. The moment that a child is created, this function scans the graph for any uncovered edges and greedily adds the single best vertex that covers the most of these missing edges. This is repeated until the solution is at 100% valid, and this ensures that we only are ever comparing valid working covers. Finally, we have the smart mutation. This is basically our exploration part of it. It randomly adds a random vertex, or more importantly, it tries to remove a vertex. It can remove a vertex and a cover is still valid, then it keeps that change. This is how the algorithm discovers small solutions and explores more potential solution spaces. Now we have our second algorithm, the genetic algorithm enhanced with the wisdom of a crowd hybrid. This is our smart competitor to our first algorithm, otherwise the exploiter. The philosophy here is that it reduces the dumb chance of randomness of the standard genetic algorithm and it injects it with some type of competency. It's identical to the standard genetic algorithm in the sense that it uses the same selection, crossover, and mutation, but it pauses the evolution every 50 generations to run a special enhancement. This can be broken down into three parts. First, it selects the experts. It sorts the entire population by fitness and takes the top 20%. These are the best solutions found by far in the standard genetic algorithm. Second, it aggregates its wisdom. So this is the core of the wisdom of crowds. My code iterates through all these expert solutions and counts the frequency of each vertex. For example, it might find vertex 15 that appears in 90% of the expert solutions, while vertex 7 only appears in 10%. This counts gives us a score of how essential each vertex might be to the solution. And third, it injects the wisdom back into the population. And so it builds a brand new wisdom cover by selecting all vertices that met a 30% agreement threshold. It's not just copying one expert, it's building like a new solution based on a collective agreement, something that is found in a lot of these expert solutions. And just like the standard genetic algorithm, this solution is often invalid, so it must be passed through the greedy repair. This new repaired better wise solution then replaces the worst individual in the population. This is where it's pure exploitation. It forces the population to stop exploring and instead focuses on the best and most promising areas that experts have already identified. This should make it converge faster and essentially more reliable. So enough of all the explanation. I will get to running the entire experiment. So this is my source code, source.py, and it will run both algorithms 5 times on 5 graphs. This usually takes about 35 to 40 seconds to generate all the data and plots and stuff. I'll start it now. Yeah, usually about 35-40 seconds, but as it's running, you can see it is logging each algorithm and each individual generation. As you can see, with every generation, it's finding a better and better solution, and it's starting with like graph 20, then it goes to graph 30, such and such, and it works its way up to graph 60. For the standard genetic algorithm, you just see generational updates, but eventually when it gets to the genetic algorithm plus the wisdom of crowds, you can clearly see the WOC enhancement log firing about every 50 generations, and it injects its new wisdom solution. Now it's finished, and it was able to generate all of the graphs and plots and stuff. It's complete, and the script has saved all the plots and it generated its final results table, and so we can now go and analyze these data. So I also want to show that our program also generated different graphs. So this is the comparison convergence graph for the 20 vertices, 30 vertices, 40, 50, and 60. As mentioned earlier, we also are comparing using the two algorithms are comparing the same data, so we know it's so we can compare it fairly. And they also generated vertex covers. As you can see, these are the best solutions where we take all the nodes that the smallest amount of nodes that connect all the edges. Obviously for the 60 vertices, it's crazy. There's 60 vertices but 307 edges that it all connects together, and so it's pretty interesting find. So now we have the final summary table from the run we just did. Now, the first thing you might notice is that these results are messy. They are not simple and not the clean A beats B in every case. This is exactly why this is a good and realistic experiment, because not everything is set in stone and clear cut, and this is why it's so interesting. In the real world, especially when you're tackling an NP problem where there are no perfect solution, you don't get clean wins. So you get more complex, nuanced data that you have to interpret, like the one we have here. So for example, on graph 20 and graph 40, it was a perfect tie. Both algorithms found the exact same solution with zero standard deviation. This tells us that on these specific graphs, the problem was either too simple to find the optimal solution, or more likely than not, they both converge at the same time, creating like a strong local best solution. This gives us a pretty good baseline. But the real story is that there's one algorithm that shows more character out of the two, and so in these three graphs we see a clear statistical difference in their performance. This takes us to our finding. My first major finding is what I expected. The wisdom of crowd hybrid is more reliable. This is not to say that it was way better than the standard genetic algorithm. It just means that it was more reliable in some cases. But I mean, if you can see, they yield pretty similar results, and so it's not way better. But for the sake of the project, the wisdom of crowd is more reliable, and so it's for our conclusion. It's just more reliable. Let's look at the data for graph 60, our largest and most complex problem. The minimum score is 44 for both, which is a key detail. It means that both algorithms are capable of finding the same high quality solutions. But that's not the whole story. Look at the average and standard deviation columns. The standard genetic algorithm had an average of 44.4. This means that in its 5 runs, it had unlucky streaks. We can see from its max of 45 that it's pure randomness. The lucky chance of exploration sometimes led to a worse solution. In this case, exploration was a kind of a liability. Now we can look at the genetic algorithm enhanced with the wisdom of crowds. It had a better average of 44.2 and a lower standard deviation. This proves that the exploitation strategy worked. It successfully used the wisdom of experts to eliminate the bad unlucky runs. It basically pruned the search space and stayed focused on the high quality solutions. This is a clear win for wisdom of crowds in terms of consistency and average performance. Basically, it's the algorithm you would trust to give you a more good, reliable answer every time. But I would want to mention that they're both both are capable of finding the same high quality solution. But here on our second finding, we find the single most important finding of this entire project. This is what makes it so realistic and the results so interesting. On graph 50, the standard genetic algorithm actually had a better average result. This is exactly the opposite of what we just saw and the opposite of what our hypothesis was. Let's look at the data. Both algorithms found the same minimum of 31, but the standard genetic algorithm had lucky runs. Random exploitation that was so good that it pulled its average down to 31.6. Its worst run was at 32, which was the best that the wisdom of crowd algorithm could do on average. Now let's look at the genetic algorithm plus wisdom of crowd algorithm that was supposed to be smarter, but in this case was consistently worse. It had an average of 31.8. The exploitation strategy found a good solution, but it got stuck. It never found the better solution that the standard genetic algorithm was able to discover through pure chance. This is a perfect data-driven example of premature convergence. The wisdom of the crowds has in specific case, the wisdom was wrong. It created an echo chamber that focused on the algorithm of a good solution, but that inherently prevented it from discovering a better one or the best one. This is exactly what happens in a real-world research. A smarter, more complex algorithm can be easily outperformed by a seemingly more dumb one, if by random chance, if it's not designed correctly. This single finding is the key takeaway of the entire experiment. But here on our second finding, we find the single most important finding of this entire project. This is what makes it so realistic and the results so interesting. On graph 50, the standard genetic algorithm actually had a better average result. This is exactly the opposite of what we just saw and the opposite of what our hypothesis was. Let's look at the data. Both algorithms found the same minimum of 31, but the standard genetic algorithm had lucky runs. Random exploration that was so good that it pulled its average down to 31.6. Its worst run was at 32, which was the best that the wisdom of crowd algorithm could do on average. Now let's look at the genetic algorithm plus wisdom of crowd algorithm that was supposed to be smarter, but in this case was consistently worse. It had an average of 31.8. The exploitation strategy found a good solution, but it got stuck. It never found the better solution that the standard genetic algorithm was able to discover through pure chance. This is a perfect data-driven example of premature convergence. The wisdom of the crowds has in specific case, the wisdom was wrong. It created an echo chamber that focused on the algorithm of a good solution, but that inherently prevented it from discovering a better one or the best one. This is exactly what happens in a real-world research. A smarter, more complex algorithm can be easily outperformed by a seemingly more dumb one, if by random chance, if it's not designed correctly. This single finding is the key takeaway of the entire experiment. So the big question is why? This experiment perfectly captures the fundamental trade-offs of all heuristic designs. Something that is central to computer science, the concepts of exploration and exploitation. The standard genetic algorithm, or Explorer, is less reliable. As we saw on graph 60, it can have bad runs and streaks. But also, as we saw on graph 50, its randomness is actually what yielded the better results. Its randomness is what allows it to make new discoveries and, in that case, a better solution. The genetic plus wisdom crowd is a tool for reliability and is more consistently reliable. As we saw in graph 60, it's great at eliminating bad runs and overall giving a better, more consistent average. But on the same hand, as we saw in graph 50, it can be like a double-edged sword. The same reliability can become its weakness, leading to a premature convergence that gets it stuck on a great solution but not the best. And because this is an NP complete problem, we don't know the perfect answer. I can't say for sure that algorithm A is better or algorithm B is better. In this case, genetic algorithm is better than the wisdom of crowds, and I just can't say. We can only say that algorithm A is more reliable, while algorithm B is the better explorer off pure chance. This experiment proves that the best algorithm truly depends on case by case and the problem itself, and you are always balancing the risk of a bad run against a run where you risk getting stuck in the good solution but not the best. So to conclude, I believe that this experiment was a complete success because the results weren't simple, they were realistic. It proved that the smarter algorithm was not the best case scenario every time. It's a powerful tool for reliability, and which makes it more valuable. We saw it win on average on like graph 30 and graph 60. However, it must be balanced. As we saw on graph 50, it can be outperformed by the standard genetic algorithm's pure lucky chance. This leads directly into future cases and work. The premature convergence on graph 50 is likely because my parameters were offset. The 20% expert pool and the 30% agreement threshold are just random or arbitrary numbers that I chose. These can be tweaked, but in this case, it made the wisdom of crowd too aggressive. The key to really solving this issue is to get the best of both worlds. Basically, we should tune the wisdom of crowds parameters to make it less aggressive. I would run this experiment again, but this time I test like a 10% expert pool to get a more like expert opinion, or I try to get a 50% agreement threshold to get a stronger consensus of all the vertices. The goal would to be to find the perfect balance, strike the perfect balance between algorithm A and algorithm B, make the wisdom crowd less aggressive so that it becomes more reliable, and maybe rely more on chance, as we saw on graph 60. Without the premature convergence, we saw on graph 50. We can see the balance between the two. In conclusion, this is a pretty fun project for me, and it gave me a clear data-driven look on the concepts we learned in class, and it really shows that messy results can be, the ones where we learn the most, or the most insightful ones. Thank you for watching, and as always, if you have any questions, please feel free to reach out to me, and I'm always down to discover and discuss these findings.